Let's take a look at the second lecture that we're going to have. This one's going to look at asphalt pavement materials. The topics we're going to cover in this lecture are going to be fine aggregates, coarse aggregates, blended aggregate specifications, the Marshall method, the weighted average method for aggregate blending, the high beam method, and the super pave mix design. If we take a look at the fine aggregate, and the fine aggregate angularity is measured by pouring a dry sample into a cylinder of a known volume. The mass of the sand in the cylinder is measured. The mass of the sand that the cylinder would hold if there were no air voids can be calculated from the bulk relative density or the specific gravity of the sand. From this point, we can calculate or determine the percent air voids in the sand. And in the PowerPoint presentations, you'll be able to look at an example that'll take you through this on how to determine the air voids. If we look at the coarse aggregate, the amount of thin or elongated particles in a sample of coarse aggregate from gravel source is measured by examining a sample of the aggregate. The length of each particle is measured by its width or thickness, and the least measured value is utilized. If the length is over 5 times the magnitude of the second measurement, it is considered a flat or elongated particle. These particles may break when being mixed into an asphalt concrete or within the overall paving process or operation, leaving particles that are not properly coated within the overall binder material. Super pave requirements indicate that the percent of flat or elongated particles shall not exceed 10% of any pavement with an ESAL of over 1 million. And again, what we're looking at is anything as it gets longer, it's going to snap on us, and if it snaps, it's going to create a failure problem within the pavement, and this is what we're trying to avoid. The clay content of the aggregate, the clay content of the fine aggregate is measured by the sand equivalent test that was covered in our module 4 that we looked at. The sand equivalent values must meet the following minimums according to the super pave standards. So again, we're looking at that traffic. We have less than 3 million. Do we have 3 to 30 million, or do we have more than 30 million? And then our minimum sand equivalent value would then be, of course, for less than 3 million, we want 40%, 3 to 30 million, we want 45%, and of course, if it's greater than 30 million, we want 50%. Asphalt concrete design mix. The design of an asphalt concrete mixture includes the selection of the best blend of aggregate that will meet the design specifications for the optimum asphalt content that is also economically cost effective based on the environmental elements it must withstand. And we discussed this already. Different parts of the country, we're going to have different specifications and standards to handle the environmental conditions that the road surface is going to be placed within. So of course, number 1 here, standard mix design includes the following steps. We get the selection of the aggregate proportions to meet the specifications that we're looking at. Again, we talked about compaction, soil analysis, investigations, and all this good stuff. We want to conduct trial mixes at a range of asphalt contents and measuring the resulting physical properties of the samples. We then want to analyze the results to obtain the optimum asphalt content and to determine if the specifications can be met. We repeat these until or with additional trial mixes using different aggregate blends until a suitable design is found. The 2 most common methods for making and evaluating trial mixes are the Marshall and the high beam method. The super pave method developed by the Strategic Highway Research Program, of course, is becoming a standard method. When we look to blend aggregate specifications, again, we trying to put these aggregates together as our base so that these particles move together and provide us with a strong surface that's going to be durable over time. So the specifications for the gradation of the blended aggregates in asphalt concrete vary considerably. Again, we're not going to have perfect aggregate particles, so we're going to have to take that into consideration. A number of gradation specifications for various types of asphalt materials and for different types of pavements are provided in the ASTM standard D3515. Typical specifications for base and surface courses are provided within the following table. Of course, you're going to see that within the PowerPoint presentations. The first step in the mix design is to select the proportions of the proposed aggregates, including the mineral fillers that will produce the combined gradation that is close to the center of the specification limits using a blending method that has been previously discussed. Either the Marshall or the high beam method can be employed to make the first trial mix. If we look at the Marshall method, aggregates are blended in proportions that meet, of course, the specifications. Mixing and compacting temperatures for the asphalt cement being used are obtained from temperature viscosity graphs. These temperatures are those required to produce viscosities of 1.7 plus or minus 0.2 square centimeters per second, or 170 plus or minus 20 centistrokes for mixing. And of course, compacting requirements, 2.8 again, plus or minus our 0.3 square centimeters, or 280 plus or minus 30 centistrokes. We then look at the number of briquettes are mixed using 1,200 grams of aggregates and asphalt cement content at various percentages, both above and below the expected optimum. The briquettes dimensions are 4 inches in diameter and 2.5 inches in height. For surface courses with a half-inch aggregate, the expected optimum content should be around 6.5%. With this in mind, briquettes would be made up of 5.5, 6, 6.5, 7, and 7.5% asphalt cement. Density of the briquette is measured to allow calculations of the void properties. The briquettes are heated to 60 degrees Celsius. Stability and flow values are obtained in a compression test in the Marshall apparatus in order to measure the strength and flexibility. The stability is the maximum load the briquette can carry. The flow is the compression that the sample undergoes between no load and maximum load within the compression test. The results of the Marshall test are plotted on graphs, and density, stability, flow, air voids, VMAs, and VFAs are plotted against the asphalt content. The following are the typical relationships that can be observed. And again, you're going to see these in the PowerPoint presentation. So the density initially increases with the asphalt content until the maximum density is reached. And once this occurs, the density decreases due to the lighter asphalt particles replacing some of the aggregate, causing them to move further apart. The stability increases and then decreases on a curve similar to the density due to the fact that the strength is mainly a function of friction between the grains of the aggregate as it is related to the density. And we talked about this during the compaction lecture that we had. The flow increases along with the asphalt content as the friction between the particles decreases with thicker asphalt films. The percentage of air voids decreases as the asphalt content increases due to the fact that the asphalt tends to fill all void spaces. The percent of voids in the mineral aggregate is approximately opposite to the density curve, as the mass of the aggregate is the main component of the total mass of the mix. The percent of voids filled with the asphalt increases with the asphalt content. The optimum asphalt content is one that is economically and safely satisfies all specification requirements. The Asphalt Institute suggested specifications are shown in the following tables for the Marshall method based on the traffic flow and the minimum VMAs. And again, those tables are going to be found in the lecture presentation. So some of the scripts, or the superscripts, meaning, so we get one, standard specifications for wire cloth for testing procedures, and we're going to look at ASTM E11 and the AASH TO M92. The nominal maximum particle size is one size larger than the first sieve to remain more than 10%, and interpolate minimum voids in the mineral aggregate, or the VMA, for designed air voids values between those listed. Let's take a look at the high beam method. And of course, as mentioned earlier, this is the next most common method employed for asphalt mix in this part of the world, or North America. And the steps are that we obtain the estimated optimum asphalt content by the centrifuge kerosene equivalent method. We prepare the test briquettes at a range of asphalt contents above and below the optimum or estimated optimum. We conduct the stabilometer test to obtain stabilometer values in the high beam apparatus. We conduct swell tests on 2 samples containing the estimated optimum asphalt content. We then look at the detailed procedures, or the detailed procedures can be found in the Asphalt Institute's mixed design methods for asphalt concrete, and that's MS2. The laboratory design includes the proportions of aggregate, binder, filler, or other additives for the asphalt mixture. The temperature range for the plant operations, along with the quality controls required to produce the final product, are also taken into consideration. And again, the following tables, you can find these in the PowerPoint presentation, are based on the high beam method. And here are some suggested criteria for asphalt concrete design, again by the high beam method. So we look at the stabilometer, the swell, inches and millimeters, the percent voids that are recommended, and we look at, is it heavy traffic, medium, or light, and so on. And then we make our selections from there. Let's take a look at the super paved mixed design. And the asphalt pavement has been one of the major areas of study under the Strategic Highway Research Program. And again, makes sense because we're trying to develop road surfaces that are going to withstand the environment and time that they're being used. So the major changes in the standards, the test methods, design procedures have been recommended based on research information. Testing and design procedures will more closely simulate the actual loading and climatic conditions that the pavement surfaces will endure. And again, this is important. Discussed it before, which is North America here. My area of the country, New Jersey, has different environmental conditions than Arizona would have, or the state of Washington, or Florida, or Missouri, or any of these other states. So we want to try to get them conditions as close as possible so that we can have a road surface that's going to withstand a lot of these environmental conditions. So these changes are being updated, or adopted, I should say, by most of the highway authorities as soon as the new equipment is obtained and pavement standards and specifications are updated. And the SHRP asphalt recommendations are designated the super pave method. The new super pave standards for asphalt binders and aggregate have been discussed, and of course covered in the mixed design procedures. The super pave mixed design method is a performance-based method that utilizes testing and evaluation procedures simulate by actual field conditions. Of course, we have 3 levels of mixed designs are outlined and considered. We get level 1 is suggested for low volume roads up to 1 million ESALs. Level 2 is recommended for medium volume traffic with an ESAL of 1 to 10 million. Level 3 is for high volume traffic road volumes and for critical situations that take into consideration exposure to extreme temperatures or where risk of pavement failure must be reduced to a minimum. Acceptance for the level 1 standards is the first requirement for all levels. Level 2 and 3 use samples that have been developed in the level 1 testing. In the level 1 procedures, aggregate and binder are tested and checked for acceptance. The trial mixes are produced and tested in level 1 are compacted in the super pave gyratory compactor at a gyration angle of 1.25 degrees. The vertical pressure for compaction is 78 psi. The number of compaction blows and the temperature of the material during compaction varies according to the design requirements and, of course, specification. The Superpaver gyratory compactor has a control and data recording panel, has a compaction mold that is 15 centimeters in diameter, and a compacted sample. The samples are larger than the ones produced by the Marshall test. The following steps in the Level 1 mix design procedures are adopted from the Asphalt Institute's Level 1 mix design manual, or the SP2. So one is determine the total ESAL design traffic load with the average design high temperature and maximum size aggregate to be used. We then select the asphalt binder grade. We then select the the aggregate blend that we're going to use. And of course, we want to make sure that the aggregate must meet the gradation and quality requirements with the 3 blends of aggregate selected for the initial trial. We then want to select the trial asphalt binder content. And of course, the content includes both the absorbed and effective asphalt values that we have. The quantities can be calculated using the following relationships: the bulk and apparent relative densities of the aggregate, the relative density of the asphalt, the approximate proportions of these materials in the mix, the size of the aggregate based on the Asphalt Institute manual. And for normal aggregate, the main factors are the aggregate size and its asphalt absorption. The asphalt absorption is assumed to be 60 to 80% of the water absorption. And of course, the following tables can be used, and you're going to see these in the PowerPoint presentations. So we're looking at that estimated asphalt binder content. Again, what's the aggregate nominal size? And of course, we're looking at that relative density and absorption. We move on to step 5 here. So we're going to determine the mixing and compaction temperatures from the temperature viscosity charts, or for the modified asphalt binders from the manufacturer's recommendations. So the mixing viscosities are between 0.15 and 0.19. Compaction viscosities are between 0.25 and 0.31. We're then going to take and prepare the aggregate samples that we're going to look at. So we get 2 briquettes, or each requiring 4,700 grams are recommended for each blend. So another sample of 1.52, 2.5 kilograms is needed to determine the maximum density of each mix for the 9.5, 12.5, 19, and the 25 millimeter aggregates that we have. And about 3,700 grams are needed for the moisture sensitivity test. We move on to step 7 here. We determine the compactive effort to be used from the following table. Of course, that's going to be in the PowerPoint presentations. The briquettes must be compacted with the maximum number of gyrations in the compactor. And of course, we look at the N of the design data is used for the calculations of volumetric properties. And we get the N, or the initial, and the N of the max values measures the compatibility of the mix. We then heat the aggregate and asphalt binder to the mixing temperature and the mix. We then place the mixed samples in an oven at 135 degrees Celsius for a short-term aging, or we remove the heat after 4 hours. And then, of course, we bring the samples to the compacting temperature and compact with the N maximum gyrations that we are looking to meet or have. And of course, the height of the briquette is measured or recorded for each gyration. We then look to calculate the density of each briquette using the density and the height of the briquette at N maximum gyrations. Calculate the densities, of course, at the design and the initial. We determine the maximum bulk density based on the AASHTO T209 of the mix using the sample of loose materials, and determine corrected densities at the design and at the initial. We calculate the air void content, the VMAs, the VFA, and of course at the design densities. We estimate the asphalt content at 4% air voids by subtracting the value of 0.4 times 4 minus the air void percentage from the percent asphalt mixed. Correct values for the VMAs and the VFAs. The corrected values for the VMA is the initial value, and then we get that value of 0.1 times 4 minus the air void percentages. And of course, we look at that and contents for other values that we have. And the VFA's values can be found from the VMA minus 4.0 divided by the VMAs. We take a look here. We now want to check the corrected VMAs and the VFAs results from each blend for compliance with the specifications given in the tables for the VMAs and the VFA criteria. The two tables for the VMA and the VFA criteria will follow at the end of the slides, or of course you'll see it in the PowerPoint presentation. We then look at the density at the initial must be less than 89% of the maximum density to ensure that there is a strong structure to resist rutting. The density at the max must be less than 98% of the maximum density to ensure that the minimum of 2% air voids remains in the pavement in its densest condition. The sample for the moisture sensitivity is tested. Again, AASHTO T283 we're looking at. And the tensile strength of a saturated sample must be a minimum of 80% of the tensile for the control sample that we have or used or looked at. We want to know what the value for the dust content, so we want to calculate that. And of course, the percentage of the aggregate passing the 0.075 millimeter divided by the effective asphalt content as a percent of the total mix. The dust proportions must be between 0.6 and 1.2. If none of the aggregate blends tested meet the specifications, adequately select other blends of aggregate for further trials that we're going to do. So we then look for an acceptable blend has been determined. New samples are made for asphalt contents, and the estimated content of 4% air voids and contents that are 0.5% less and 0.5 and 1.0% greater than the estimated value. We then do the final air voids. We look for the VMAs, the VFAs. Results are plotted, and the asphalt content at 4% air voids is acceptable for other properties is used for the reductions of our or level 2 and level 3 test. This concludes the Module 3 lecture on asphalt pavements and materials. So again, please look at the PowerPoint presentations. Examples have been completed, and you'll be able to use them to complete any homework assignments that require calculations.